So this talk is about how can we build a zkVM in a way that's agnostic of the proving system, which is something that we're concerned with at Powdr. So let me give you a very quick introduction. So at Powdr, we kind of have a DSL to describe a VM, and it looks like this. The user can declare some registers and some instructions, and then provide an assembly program using these registers and instructions. And then that compiles to a zkVM. But we want to do this in a way that is agnostic of the proving system. Obviously, this zkVM is extremely simple and kind of useless. But we also have an implementation of RISC-V, for example, but you could also imagine zkEVM. Yeah, and that would take a few hundred lines of code in this language. But this talk is going to be more about the low level, so let me walk you through the compiler pipeline. So on the left-hand side, you see the high-level description, and the first step would be to compile to PIL. PIL stands for Polynomial Identity Language, and has originally been developed by Polygon, and describes some low-level constraints. And then from PIL, we can compile to different proving systems. An obvious choice is SNARKs, because that was the original use case by Polygon. But this talk is going to be about how can we also go towards folding-based backends or GKR. So in order to explain that, let's go through some of the details of PIL. So this, of course, I'm going to explain this using Fibonacci. And so on the left-hand side, you see a very simple PIL program that describes a Fibonacci computation. On the right-hand side, you see the corresponding execution trace. So in the first two lines, the program declares two fixed columns. And fixed columns are columns of the execution trace that have a fixed value. So the values are fixed ones at setup time, and the prover cannot change them. And in this case, they're only used to indicate whether we are currently in the first column or the last column. And then there are two witness columns. And witness columns can be filled with any value by the prover, but they're subject to some constraints. And so if we look at the constraints, for example, the first two constraints essentially force the prover to initialize the Fibonacci sequence correctly with the values 1 and 1. And you can see that we have to multiply with this is first column, because one property of constraints is that they always have to be satisfied in all rows of the execution trace. And then the next two constraints basically force the prover to update the Fibonacci sequence correctly. And you can see that we have this next operator, which is kind of this prime operator, which means that we're not referencing the value of x in the current row, but in the next row. So that's mostly the abstractions that we have. So just to recap, there's columns, which can be fixed or witness columns. There are constraints, which involve additions and multiplications, and they can have a next operator. And they need to be satisfied in all rows of execution trace. And one thing I haven't yet talked about is verifier challenges, which are just random field elements that are sampled by the verifier after some witness columns have been committed. And this is useful to implement lookup and permutation arguments and other things. And here you can see an example of how you would implement a permutation argument. So let's go through all the proving systems. And first up, SNARK. As mentioned before, this is the most straightforward one, because that's kind of what PIL was designed for. And I don't want to spend too much time on it, but basically a SNARK is going to interpolate a polynomial for each column of execution trace. And this is my attempt at drawing these polynomials. And then the constraints just become constraints on these polynomials, and SNARKs are designed to prove that constraints on polynomials are satisfied. And next up is folding-based backends. So what are folding schemes? So one thing they do is they provide for incrementally verifiable computation, which means that you start out with some initial state, which you can think of as just a small vector of field elements, and then you keep repeating the application of a function, which is a fixed function. It's always the same function in each step until you end up with some final state, and that's the result of your computation. And this function, at least in the simple cases, should be the same in each step of the computation. And that is kind of similar to PIL, which has the same constraints on all rows of the execution trace. So if we look at a simplified version of this Fibonacci program, here it's the same program as before, but I left out his first and his last column because folding schemes kind of have a native way to represent the first and last state. But given these constraints, we can essentially extract a function f that computes the next row from the current row. And so we can view the execution trace as a collection of intermediate states where each row has been computed by the function f from the previous row. And so if we view it like this, then that fits into this IVC scheme, and then we can compile to a folding-based backend. And last but not least, GKR. So GKR is another protocol that proves correct computation of a shallow layered arithmetic circuit. So let's go through each of these terms. So an arithmetic circuit is a circuit that computes something just using additions and multiplications. And a layered circuit means that each node in the circuit can be assigned to a layer number, and then you can only receive inputs from the previous layer. And by shallow, we mean that the number of layers should be small, which is important because the verification time is going to depend, it's going to be proportional to the number of layers. So in particular, the number of layers should not depend too much on the size of the input layer, for example. And another property that's desirable if it's a structured computation, which you can see here. So you can see here it's not an arbitrary circuit, it's many copies of a small subcircuit. So it's kind of describing a data parallel computation. It's applying the same function to different inputs. And eventually, all these layers, the value of these layers are going to be represented as polynomials, and the verifier needs to be able to evaluate these polynomials, but only for the input layer and the output layer, which typically means that for the input layer, there's going to be some polynomial commitment scheme, and for the output layer, it could also be committed, or it could be easy to evaluate by the verifier for some other reason. So that's it for background. Let's look into how does it all relate to PIL, and how can we take a PIL program and compile to GKR. So in this extremely simple program, we just have two columns and one constraint. And the idea is kind of to just put a concatenation of all the rows of the execution trace and put them into the input layer. And then the constraint needs to be satisfied in all of the rows, so we can instantiate a small arithmetic circuit many times that just evaluates the left-hand side of this constraint. And if and only if all the constraints are satisfied, the output layer would just be the vector of whole zeros, which is encoded as the zero polynomial, so it's trivial to evaluate by the verifier. And that's it. So just to recap, I kind of view PIL as a language to express constraints on vectors of field elements, which is kind of a data parallel way to describe computation. And yeah, like a structured computation that is exploited by different proving schemes but in different ways, but we can kind of compile to all of them, or at least the ones I've mentioned. And yeah, that's nice because then you can describe your zkVM once and decide on the proving system later, or even prove different parts of the zkVM with different proving systems. Time for questions.